So today we're going to talk about the simplex method. So finally, after much I advertisement, I'll tell you how it works. But the thing is, like, we already have in place like most of the like material, like the concepts needed, so you won't find it that difficult. It's kind of like doing like what is it? Row reducing a matrix, but in a slightly different way. But you'll see it's not that different from that. So it will have like a familiar flavor to it. So again, it is kind of like a natural thing to try. What's kind of surprising is that it works as well as it works. Like, so just to like, I will use the simplex method for like this example we had worked on the very first day of class. If you remember the farmer's problem, so I'll show you how to solve that in that case using the simplex method because it's kind of like simple enough that you can see all the details. And then we can extract kind of like some like main features that will happen. Uh, so just to kind of like, I'll kind of write like what the optimization problem was in this like example with the farmer, but just to show you what we had discussed, um, you know, we you could either sell potatoes or carrots, and you had some from constraints coming from the amount of potato seeds or carrot seeds that you had and the amount of fertilizer that you had. And again, I'll write kind of like those constraints back on the PDF, but the idea is that if you drew them, you know if you drew all the constraints, like you had like this polyhedron, and if you kind of check the corners and like the max for the function that we were working with, which was this one, um, was maximized at this corner. Okay, so this is where the max occur. And I'll kind of show, and we had done it graphically the first day of class. I'll show you how it works from the perspective of the simplex method. So first I'll kind of like write what we need to know. The only thing is that here, if you see like everything is measured in thousands, I'll just work with 5,435 instead of 3,000, 5,000 and things like that, because like otherwise it's too many zeros that I have to keep track of. So I'll divide all those numbers by 1,000, but it is really the same example that we had worked with on the farmer's problem. Um, so back to the farmer's problem. So in that case, again, we were trying to find the max. I'll write it in the usual notation we had. We are trying to find the max of 1.2 x1 plus 1.7 x2 subject to x1 greater or equal to 0, x2 greater or equal to 0. And then the constraints again, if you divide all of them by 1,000, the constraints are that x1 is less or equal to 3, that x2 is less or equal to 4, and that x1 plus x2 is less or equal to 5. Okay? And what we had found graphically, we knew that graphically the region is what I just showed you. So the region kind of looks like this. This is like the polyhedron in 2 dimensions. And at this corner, oops, this was the corner where the max occurred. That corner was, if I'm not mistaken, 1,4. So basically and again, we had done that like using the simplex method. What I'll show you is, and I'll draw that picture on the board so that you can refer to it and see what is going to be happening. But I'll, basically what I'll show you is how the method like would find that corner in a again for this type of problems in an efficient way, uh, which does not require like listing all the corners and verifying all the corners. That's kind of like the advantage. We're going to locate this max without having to kind of like go through all the corners in the problem, which is how what you would need to do if you were to kind of just list everything out because it's just like literally like a spreadsheet. So what the simplex method does is find the max or the mean. But as I told you, every mean problem can be turned into a max problem. So like you kind of choose how you want to work with it. I'll go with max because that's how I had motivated it before. Um, or mean without having to go through all the corners in a sense, or to examine all the corners. Okay. So I'll give it is an algorithm, so I'll try to kind of like present it as an algorithm with steps because it's the example, maybe a little bit less formal, but then I'll summarize everything. So kind of like kind of something that you would program, like if you wanted to do like a computer program for this, like you know, that's kind of what you would do. So if you want, you can call this step zero. It's just like to rewrite the system in like equation form, right? Um, rewrite the optimization problem in equation form. Or like that's sometimes also called like the standard form or canonical form. There are many names for it. So if you go back to here, like we already know how to do that, right? Like for this inequality, add like a slack variable. For this inequality, add a slack variable. For this inequality, add a slack variable. So we end up with three slack variables, and like there are three inequalities that become three equations. So we will have like a matrix with. Well, I'll write it first as a you know I'll just write all right. I'll copy paste this, but like, really the only thing that's going to change is like the conditions that the fact that you have three more variables, which are the slack ones, and these are changed into equalities, right? So it would be x3 equals 3, x4 equals 4, and then plus x2 plus x5 equals 5. So in matrix form, which is what I care about, how does this look like? So there are three equations, 5 variables, so it's going to be a 3 by 5 matrix, right? So the coefficients are 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, and then 1, 1, 0, 0, 1, right? This is the matrix times x1, x2, x3, x4, x5 equals 3, 4, 5. Is that okay? So far, so good. Everything making sense here. So I'll just kind of write the important thing that A is 3 by 5, and that B is, well, I guess 3 by 1. That's less important, and X is here 5 by 1. Okay. So step 0 is just like the rewriting, which in many problems, like it may just be written already in equation form. So like that's why I'm calling it step 0, because it's not something that you may necessarily do every single time. Okay, and now comes like the fun part. So step 1, which is like the real first step, is that you have to find at least one basic feasible solution. Okay. Step 1, find at least, well, find one basic feasible solution. Like you one basic Okay. And this step actually sometimes is not entirely obvious, and so we will later revisit how would you do that. So sometimes it is not super clear how to find a basic feasible solution, but when the problem comes from this inequality format, it's actually many times like there's like a natural one. But let me just put it in parentheses. We'll discuss later how to do this when it's not super obvious. Like we'll discuss this, discuss how to find them if it's not clear, if to find them, if it's not obvious. Okay, but in this case, how do you find a basic solution? If you remember, you have to find a basis for the matrix, right? Because the matrix is 3 by 5, you need a square matrix, which would be a 3 by 3. So you need to find a 3 by 3 invertible matrix out of the matrix A. And I'm saying that in this case, there's kind of like an obvious choice. I don't know if anyone can tell what's like yeah. Right. Like hidden in this, it's kind of like the identity matrix, right? And that kind of like happens when, like, if you always have to add like a slack variable to each inequality, there's always kind of like the last columns are always like the identity. So that's why I'm saying that in many cases, it's kind of like already natural how to find a basic solution. But yeah, in this case, for this matrix, like the basic, like the natural choice for our matrix is like the last three columns is what? Columns 3, columns 4, columns 5, because then like you're just dealing with the identity, right? And what you're doing with the identity, finding the basic solution is like almost like trivial, right? Because like there's no system to solve, right? Like you have to solve this times x3, x4, x5, right? And that equals 3, 4, 5. But that already tells you what the values for x3, x4, x5 are, and then the basic solution is just that with zeros everywhere else, right? So the basic the kind of like this is like where the algorithm will initialize in a sense. So the basic solution is 0, 0, 3, 4, 5. Is that okay? Is that making sense? Um, by the way, and this is why I wanted the diagram, you know, for you to kind of access it, because this basic solution, again, this lives in 5 dimensions, right? This lives in 5D, lives in R5, what you call R5, right? But in this case, if you look at the shadow, right, like the shadow like corresponds to that diagram that we had at the farmer's problem. So like the shadow, if you just keep track of the first two entries, that's 0, 0. So like the algorithm is initializing at the origin in this case. Okay, so that's where like the algorithm starts. So like the shadow is 0, 0. So our like the method kind of like is going to start at the origin and find the maximum corner, which should be like the one that you see on the picture. So that is where the method starts, or the algorithm, right, begins. Okay, so far so good. Now here's another remark, which maybe you remember from. So there's like a way to do this using only matrices, which is what I will explain in a moment, but I'll stick more with um, I'll stick first with like the presentation with like the actual equations, because it's kind of like then that's kind of makes it more natural to see how the matrices appear. So, but if you remember, so just also like a remark from linear algebra. So if you have a system of equations, if you have ax equals b, right? Um, So again, we have talked this about this before, but when you have a system of equations, either it has no solutions, a unique solution, or infinitely many solutions, right? What I had mentioned is that we are kind of already, because of the assumptions in this class, we're always in the infinitely many solutions case. That's the only thing that's interesting, other, because if there's like a unique solution, okay, there's only one thing to look for. If there's like a max or a min, that's not interesting. And if there's no solution, okay, there's nothing to maximize or minimize over, right? Like, so you really are stuck in the unique infinite many solutions case. But if you remember, there's like a result from linear algebra that says that in this case, there's like a certain number of free variables, and the number of free variables is like the number of variables minus the rank. Okay, so number of free, and I'll kind of show you how that looks like in this case. Equals the number of variables minus the rank. What that means is that you can always express, you know, like the idea is like you can always express the solutions in terms of like then any solution can be expressed in terms of like the free variables. Okay. In our case, right? Uh, the number of variables is 5, right? We have 5 variables, and the rank is 3, because I told you we are always working with a matrix of full rank, which means that the rank is the number of rows. So that means that there are 2 free variables, okay? And so what I'm going to do, what that means is that I can write all the variables in terms of you know, like I can write everything in terms of 2 variables. So what I'll do, and if you want, you can call this step 2, is that I will rewrite the equation, the system of equations, so that the basic variables are solved in terms of the non-basic variables. And this needs some explanation so that you see what I mean. Okay. So again, let me explain what's going on here. So, oops, what was the system of equations we were working with? And again, I'm not going to use matrix notation for now, but later I'll tell you how to rewrite all of this in matrix notation. But the system of equations we had was x1 plus x3 equals 3, x2 plus x4 equals 4, right? And x1 plus x2 plus x5 equals 5. Bless you. So that's what the system of equations that we had. And if you look at this system, it's very symmetric, right? Because like kind of like all the variables, like none of the variables is solved in terms of the other, right? Like they kind of like all appear very like in a very symmetric way. What this is saying, like in this step, what you're saying is that, okay, you made a choice of basic variables when you find like the basis, right? When you find the basis, in this case, you chose like x3, x4, and x5 to be the basic variables, right? So what the step says is like rewrite like the equations that you found in terms of x3 equals something, x4 equals something, x5 equals something. So you kind of break the symmetry and solve for like the basic variables. So for example, here, our basic variables are x3, x4, x5. So I'll solve the equations for those variables. So I'll solve for those. So how does that look like in this case? It looks x3 equals 3 minus x1, x4 equals 4 minus x2, right? And x5 equals 5 minus x1 minus x2. So you see, like the basic like it's kind of important to maybe put this like on the left hand side. Like the basic variables are being written in terms of the non-basic ones. So the non-basic ones in this case are x1 and x2. And how many of those are there? There are two, which is like the number of free variables. So it's all kind of like consistent if you think about it. Is that making sense so far so good? So it's kind of like just like a relate, like we haven't touched the system of equations. We're just like rewriting it to think about it in a different way. So it's kind of like a completely psychological. There's nothing changing with the equations. They're exactly the same equations. So the other step, which I mean, again, maybe the step, like the numbers of the steps, I will change them later. Or you can call this 2.2 or like if you want, because it's kind of like still the same. You also have to rewrite the quantity you're maximizing in terms of the non-basic variables. So you rewrite the quantity you're maximizing in terms of the basic variables. Of non-basic variables, like, so non-basic variables. So let's give that let's give that a name because, so if you go back, sorry, just to go back for a second to the optimization problem, this is what we're trying to maximize. So let's call that Z just to give it a name, or you could call it like M for maximizing or whatever, like just call this quantity like expression or F for function, like, you can, so in our case, is what we're maximizing, is what we're maximizing. But this is already written in terms of x1 and x2, right? Which are the non-basic ones. So there's no rewriting needed. Like, right? Like there's no, this is already good because you already have x1 and x2, like the function, like the maximization stuff in terms of like the non-basic ones, which is already in terms of x of the non-basic variables. Okay. So it doesn't need to be, so you can leave it as that. So you can leave it as that. That okay? So far, so good. Okay, now here comes finally the really important part. Let's see if I can. So let's see. So here's what's happening. So like here's like the main like insight of the simplex method. So again, think about it like as an algorithm. These are the non-basic variables with the solution that you start with, right? We start at a feasible solution, right? So where is oh, here it is, a feasible solution, right? We start at this feasible solution. So the algorithm starts, when the algorithm starts, like the non-basic variables are set equal to 0, right? So the algorithm is starting at a value, and those variables are equal to value 0. So the algorithm, at the step that we are currently at, like the quantity that we're trying to maximize, it has a value of 0 because that's a value that we have given our non-basic variables. So which is kind of corresponds here in the diagram. That makes sense, because you are at the origin, and at the origin, the value of the function is 0. So we're starting kind of like at step 0, or like at this initial step, like the function is 0 and we're trying to maximize it. So we should try to increase it, right? We have to increase its value. Since it only depends on two variables, the only way to increase its value is by increasing one of the values of one of the variables, right? That's kind of like, hopefully it's clear. Now, the thing of the method is that it increases one variable at a time. So you're not allowed to change the value of the two variables simultaneously. Or like, even if there were 10,000 variables, you can only change one at a time. So the two is not important. The point is like, you think that secretly they're both equal to zero, and I'm going to change only one of those two. Okay? So the question is, which of the two should you try to increase first? And I don't know if there's anything in the function that suggests which one should you try to increase first if you're trying to maximize that as fast as possible. Yeah. Right, exactly. And that's the insight. You should try to focus first on the one with the largest coefficient, because if you change, again, pretending you don't know anything else about the values of the variables, if you change this one the most, like that would have the biggest effect on the function, right? So let me write that down. So the idea is that you want to increase only one of the two you want to increase or change the value for one of the non-basic variables, and you choose the variable with the largest coefficient in the optimizing function. Okay, and you choose the value with the largest coefficient in the optimization function. Let's call it that, in the optimization function. Okay. So in our case, that means is that we're trying to make x2 as large as possible. Okay. Yeah. Yeah. You will always choose like. Oh, well, in that case, like, right, I'm doing it for max situation. Like, it's all like turned upside down, but you can always, that's what I was saying. You can always try the max into like a mean into a max, because it's max of minus the function, right? Like, so you can always think about it as being a max problem. But yeah, because otherwise you would go kind of like the opposite way, right? So, and then you would choose like the smallest coefficient, but it's kind of like somehow it's easier to think about it in max, in terms of with max, because it is more like positive numbers, because if it's like a mean, you would try to make it as negative as you can. You see, and that's kind of more complicated than just thinking in terms of, oh, as large as you can. So, but yeah, like it doesn't, like, philosophically the same idea, so like I'll just do it like for maxes because it's easier. And if you ever have like a mean problem, you multiply by -1 and then you're done. You do the max of that, and then like you just flip all the coefficients, and then it kind of like works that way. So in our case, we try to increase x2 as much as possible. And here's like the key, because how much can we increase x2? That's like the big question. So that's why you have to go back to the equations, right? So the key question is by how much? Key question, by how much? And here's the idea. Actually, let me shrink this a little bit. Okay, so again, you have to imagine like that we are starting with the two non-basic variables set equal at 0, right? So secretly, we have x1 equals 0 and x2 equals 0, and I'm trying to just move the value for x2, because again, the rule is to only move one variable at a time. So I'm going to so just to make this, this is something that usually you can just do in your head, like once you get like practice. But so think about the, like I'm setting equal x1 to 0 here because that is not going to change from this step to the next. So I'm kind of going to rewrite the same equations, but with x1 being set equal to 0 to make it more clear that that's kind of like the stage at in which we are at. Okay. So when x1 equals 0, this is what does like the system of equations read? It reads 3x3 equals 3, x4 equals 4 minus x2, and then x5 equals 5 minus x2. And again, of course, like x2 was also equal to 0, but what we're trying to do is now change its value. So that's going to be allowed to change. So that's why I'm keeping that as a variable and not setting it equal to 0. So, okay. So so again, like you have to look at the equations and ask, okay, how much could I increase x2? Obviously, like the first one doesn't tell you anything because it doesn't involve x2, right? And then from the last, and then you look at these equations, and then you have to think, okay, these have to tell me somehow how much you can increase x2. But maybe it's not super obvious, like what the constraint is. But the constraint is that all the variables are always non-negative, right? Every variable has to be non-negative. So for example, just to give you an idea, I cannot take x2 to be 10 because if you take x2 to be 10, you get 4 minus 10, which is negative 6, you're toasted, right? So you have to look at the equations because the non-negativity forces constraints. So for example, because this has to be non-negative, that tells you from the second equation, like x2 cannot go past 4, right? And from the last equation, x2 cannot go past 5, but this one, like the second one wins because if you set x2 to be 5, then that messes up the one in the middle, right? Because you get 4 minus 5, so you would get -1. So the idea is that because of the non-negativity of the variables, you kind of notice that the best you can do is set x2 equals to 4, okay? Uh, is that making sense? Kind of. That's kind of like the key part of the problem, like because every every variable must be non-negative. The best we can do is set x2 equals to 4. Okay. And it's kind of like think about it like as a light switch where basic and non-basic is like on or off. So you kind of turn the value from 0 to 4. So it's kind of like turning it on, right? But when you turn this into 4, you force the x4 to become 0, right? So this kind of was turned off, so it became non-basic. So what we're going to do now is a swap where we're kind of like going to use this equation to kind of like change what we're thinking about, which is basic and not, and which one is non-basic, right? Because idea, again, unless the problem is degenerate, and that's why I had mentioned degeneracy before, because if there's degeneracy, then you have to be more careful. But if there's no degeneracy, the non-basic variables are the ones that are always 0, and the basic ones are the ones that are always non-zero. So what we do is kind of like a swapping operation where like now, like secretly what this is doing is forces x4 to become 0, right? So what you want to do is think about x4 as becoming non-basic. So let me write that as like, so it will become a non-basic variable. So just to write it, let's see, where am I? Step 3. So basically what you do is like, you choose the equation that gives you the maximum value for the non-basic variable you're increasing, and then you swap the variables. Okay? Yeah.
The reason it becomes non-basic no longer fills that AX equals B.
Uh, no, like basic and non-basic, like they always are solving the system of equations. Like, so it always solves AX equals B. Like what made like the variable basic versus non-basic is that whether it was, you know, we found first the basic variables and non-basic variables were set equal to 0, right? So the thing is like by, like it's think about the, Actually, in this case, it's like, if you look at the second equation, it's better to think about it in the more symmetric form. So this is kind of almost like a conservation law, because it's saying like these two variables, they're not free to be whatever they want to be. They have to add up to 4. So by increasing this one to 4, you're forcing this one to go to 0, so that the conservation is preserved. So they're all solving the system of equations, because you're still, you see, I haven't changed the system of equations at all. I haven't, nothing has happened. Like, in fact, I'm just rewriting them in funny ways, but like haven't changed the equations. So it doesn't, so it's changes like what happens is that this becomes non-basic because it becomes 0. And the non-basic variables are the ones that are 0, you see. But they're still solutions. Like, so they're always solutions. We're never missing, like we're always working with solutions of the equations. It's just that the swap it's kind of like turning a non-basic variable into a basic variable, but the trade-off is that you have to turn a basic into a non-basic. You see, it's kind of like an exchange operation. Because the number of basic variables and non-basic variables is always fixed. You know, if the matrix was 3 with 3 rows, there can only be 3 basic variables at any single step. And there has to be 2 non-basic variables. So it's just like, who do you put like into the non-basic bag and which ones you put in the basic camp? It doesn't make any sense.
Yeah, kind of.
Like this, because again, like you have 5 variables to start with, right? Any basic solution has, like, when you choose like the basis, like because it's a 3 by 3 matrix, only 3 variables are selected at a time. So you can only call 3 of the 5 variables basic, and the other ones have to be called non-basic, right? So what I'm saying is that the convention is that whenever one of the variables, like, after we found the basic ones, like the non-basic ones were made into 0. But by increasing this one to 4, you're forcing this one to become 0. So you're forcing it to become non-basic. Is that making sense? It's kind of like it is just like a game, like, it's kind of like a light switch, on, off, on, off. Every variable can be on or off at every step, and you kind of just are deciding which ones and it's kind of like the trade-off is just one at a time. So you can only swap one variable, one non-basic with one basic at a single time. Like the process like stuff works that way. Okay, so so in step 3, what you do is like use the equation that gave you the largest value for the largest value for the non-basic variable. And use this one, and use this equation to swap the roles. Okay, and use this equation to swap the roles of the variables. And again, everything, when you kind of write it in words, it sounds very contrived, but when you see it on the example, it's kind of very natural. So it's kind of like a long, very tedious explanation, but but it's kind of magical because you're really not doing anything except like rewriting these, like the equations. So what I'm saying is that in our example, it was like the second equation, right? So like the second equation said that x4 equals 4 minus x2. But again, now I want to kind of swap the role. So I now want to think of x2 being given in terms of x4. So it's kind of like just like a it is the same equation. It's just you're changing your perspective because now you're thinking of x2 as being given in terms of x4, you see? And then because now you're thinking about it in those terms, you have to make this change in every single one of the remaining equations. So it's kind of like substitute that change of information into the other ones. So you do substitute this into the other equations. So again, like just to show you what happens here, go back to the original system of equations. So there's nothing to do in the first one because like the first one didn't involve x2 at all. So that one is good. Don't touch it. The second one is just like the one that's being used for the swapping. So I'll just put like again that x2 equals 4 minus x4 now, right? And then the last one is 5 minus x1 minus x2, but x2 is 4 minus x4. Okay, is that making sense? So let's just rewrite this like a bit more simplified. So that gives you that x3 equals 3 minus x1, that x2 equals 4 minus x4, right? And that x5, okay, so 5 minus 4 is 1, right? So you get 1 minus x1 plus x4, right? Is that okay? So now I'm thinking, again, on the left side is always what you're considering basic. So now my basic variables are x3, x2, x5. So these are the ones that I'm thinking now currently as basic variables. So again, the rule of thumb, like the rule for the method is to always write the basic variables in terms of the non-basic ones. So now the non-basic ones are being considered as x1 and x4. So you see you swapped x2 with x4, okay? Is that making sense? That's a good question about it. And again, there's a feasible solution corresponding to this because the point is of the non-basic variables is that if you set them equal to 0, like this, like what is like this, like, that secretly this has already produced a new solution because there's like a solution, a new basic solution hidden here. Like, let me just make it as a remark. Not that you need to know, like, there's a new solution hidden here. Because what happens if you set, like again, like the non-basic variables are the ones that are always set equal to 0 for the solutions. So if you set x1 and x4 equal to 0, x1, 0, x4 equals 0, what do you find from the system of equations? You find that x3 equals 3, that x2 equals 4, right? And that x5 equals 1. So the solution, the basic solution associated to this selection of basic and non-basic variables is what? So x1 had to be 0, x2 had to be 4, um, x3 had to be 3, right? X4 had to be 0, and x5 had to be 1. So I'm just saying that once you have, that's like the idea. Once you have decided which ones are basic and which ones are non-basic, if you set equal to 0, the non-basic ones, that gives you the value for the basic ones, and that gives you the basic solution. Okay. Is that making sense? And what does that correspond to? That corresponds to the shadow, right? What is the shadow of this point? It's 0, 4. Where is 0, 4? If you go back to the diagram, 0, 4 is here. So now we're in this step on the simplex method. So basically the idea is like, we started here, right? We started at the origin. We had two ways to move because there were two x1 or x2 were like the two variables we could change. And the simplex method chose x2 because that increases the coefficient the most. So it moves us into the next corner, okay? And so once we do the next step, we will end up at the max. So essentially the simplex method is taking us kind of like through the path where the increase the most rapidly. So it's like a very clever thing. Is that making sense? Um, okay. It's kind of cool. I mean, but it does take some practice to get used to it, but it is like very like reasonable what you're doing. Like you just have to get used to kind of rewriting it basic versus non-basic. And once you do that, you kind of like go along with it and like the method takes care of everything. Now, so again, like but going back to all the algorithm, you at this point we're almost like we already if you write it as an algorithm, return to the previous step because the algorithm always starts at a solution, right? At a basic solution. We already are at a basic solution. So now you kind of repeat, right? So once you get here, you repeat and you just apply the algorithm again. So if you were to program this, this is like the step where you tell like the algorithm to just repeat like the previous like code, So since now we have like another solution, you can repeat the same steps as before. So I'll kind of will show you that that's indeed what I'm about to do. So since we just found a new solution, basic solution, we can, what is the word, like reiterate or, you just repeat the steps. Well, right, it's like yes, it's kind of like, yeah, but I just wanted to say, yeah, you just like, go back to step one or whatever, like I'm going, like, so you cycle through the steps again. We can we can repeat the algorithm again. Okay, so, and literally that's what I'm about to do because I'm not going to write the steps again, just to emphasize that we are just going to repeat them. So, like, just to give you a chance. So let's go back to look at the steps. So let's see. We're repeating now because, uh, right, step one was to find one basic feasible solution. We already have the new one, right? Step two is to rewrite the system of equations so that the basic variables are solved in terms of the non-basic ones, right? Like that is something we already have here. We already have the basic ones in terms of the non-basic ones. So step 1 and 2 are ready. Step 2.2, rewrite the function we're maximizing in terms of the non-basic solutions. We haven't done this yet, right? Because now x2 is no longer a non-basic solution. It's a basic solution, a basic variable. I'm not sorry about that. X2 is no longer a non-basic variable. It's a basic variable in this new interpretation. So we do have to redo step 2.2. So we have to redo step 2.2 and rewrite the optimization function in terms of the non-basic variables, which are the non-basic variables now. You can always, that's a nice thing, you can always read them from the right-hand side of the system of equations, so just x1 and x4. So again, z was 1.2 x1 plus 1.7 x2, right? But what is 1.2 x1? That's fine. We can leave it like that because x1 is still non-basic, so it's allowed to stay there. But what is 1.7 x2? X2, what is x2? X2 is 4 minus x4, right? Like that's like what we were using. Okay, is that making sense? And that, I mean, if you simplify it a little, I mean, just to, what is 1.7 times 4? That's 6.8. That's 6.8 plus 1.2 x1 minus 1.7 x4. Is that okay? Is that making sense? So far, so good. Questions up to this point? Okay, so we just finished step 2.2. So let's go back to the list of steps. The step 3 was Oh, like actually, where did I should have written these. I mean, I should have like, I'll have to write this as step 2.3, like maybe just to make it clear, let's call this step 2.3, because then what was next? You want to increase the variable, right? Like actually, let's put it here, like step 3, 2.3. You want to you choose like the largest coefficient in the optimization function, right? Because you want to continue increasing the value of the function, right? So just to go back. So again, this is the function now in terms of x1 and x4, right? You are trying to maximize it. So in order to maximize it, you want to increase the variable, like one of the two variables, because again, we're only increasing one variable at a time. So, if you increase x4, and they both start at value 0, right? Like that's how like the non-basic variables work. So you have two variables being set equal to 0. Um, and so you have to increase one of the two. If you increase the one with x4, that kind of actually drops the value for the function, right? Because like the coefficient is negative. So in this case, there's even less to think about. There's only one choice to increase, because, which is x1. So in this case, and by the way, if you set these two equal to 0, you get 6.8, which is the value of the function at this corner. That makes sense. So like, we started at value 0, now we're at value 6.8, and in the next step, we'll find this corner, and it will give us value 8, which is the max. It was 8,000 in the original farmer's problem, but I just divided everything by 1,000, so that's why. So like this method also keeps track of the value of the function, which is a cool thing as well. So it kind of like keeps track of everything for you. So yeah, let's call this step 2.3. So we decide to increase x1. We will increase x1. Right? And so same thing as before. You have to think by how much can you increase the value, right? So same question, by how much? Okay. So since so so this was a system of equations as we currently have it, right? And again, so we are going to increase x1, which means that we're going to keep x4 at its current value of 0, right? Because both are 0 at this moment. So we're going to increase x4, like we're going to keep x4 at 0. So let me just, to make it clear, more easy to see what we can do. So let me put it here. So since x4 is 0, then what do we get? We get x3 equals 3 minus x1. X2 equals 4, and then we get x5 equals 1 minus x1. And again, of the three equations, like the one in the middle tells you nothing interesting about x1, right? Um, right? The This one, the one in the middle tells you nothing interesting about x1. And so we have these two equations to play with, and we have to determine how much we can increase x1 from these two equations. Again, the restriction being that every single variable has to be non-negative, right? That's a constraint. So what would you say is the most that you can increase x1 here from? Yeah, like, right, because if you try to increase it by 3, then you mess up the last one, right? So x1 is, so what we're going to do is set up x1 equal to 1, right? And so that's being turned on at the expense of x5, right? Because x5 is like the one that has to be sacrificed now and becomes non-basic, right? It becomes 0. Um, so, and every problem is like that. Every problem of the simplex method is like that. Like it's just all that you're doing every single time, What I think, yeah, I'll kind of rewrite everything in terms of matrices, and you'll see that something really cool also happens when you rewrite all of this in terms of matrices. So then you can just work with the matrices, but it's kind of cool to see it first, like with all the variables. So we take x1 equals 1. So again, this comes at the expense of like the last equation. So we will swap it. So what does that mean that we're going to swap it using the last equation? That means that we're reversing the roles. So that means that x1 is going to be 1 minus x5. Okay? So you go back to the originals, go back to the system of equations and to swap. So go back to the system of equations and in order to do the swap. So the system of equations was this one, right? This was like the system of equations we had. Okay. And so again, what that means, in order to swap them, what that means is that every time you see x1, you replace it in as 1 minus x5. So x3 is 3 minus 1 minus x5, right? X2 is 4 minus x4. There's nothing to do there. And x5, right? X5 is 1 minus x1, but right, x1 is 1 minus x5. Oops, same wrong color. 1 minus x5 plus x4. Right, so you do the substitution because then you see everything is now written in terms of x5 and x4. And so now you're thinking of x1. Oops, sorry, then I should have written like oh sorry, where did I do the swap? I mean, I guess like oh, right. You have to be careful because like sorry, when you do the swap, like you use the fifth equation, but the fifth equation is like we including x4. So you have to put it with the x4 here. So it is 1 minus x. Oh, that's good. Like otherwise, like it wouldn't have worked, and you would have noticed like in the equation. So because otherwise you like you have to use like the or like actual equation. Like this is not like the actual equation, it's just like the equation when you use a particular value for x4. Otherwise you are changing the system of equations. So I'm glad I noticed that. So x1 is 1 minus x5 plus x4. So now we're good. We're right. So yeah, you just have to be careful about that. But once we work with matrices, that won't happen. Sorry.
Did we already say that x4 is 0?
Right, but it's not zero at every single time, right? It's only zero at this particular moment, right? So you cannot replace like an equation with like a particular, this equation is true for every value of x1, x2, x5, x1, and x4, right? If you had forgotten about x4, you're replacing the equation with which is something that only holds for a particular value of it. And you want like the replacement to kind of work regardless of which values you're going to use, if that makes sense.
Yeah.
So yeah, and like that's good to catch up. Like it's good that I made the mistake because then it's like a good point to discuss because right. The point is like it's kind of when you do Gauss-Jordan reduction of matrices, the point of like the row operations is that they never change the system of solutions, right? They're really the same equations, just rewritten in different ways. So it's kind of like the same philosophy here. This is kind of like the true equation for regardless of all the values for the variables. This is kind of like a temporary version of the equations for a specific value, but the switch cannot be done with the temporary version because you want this to work anywhere in the region, not just like in the particular area that you're analyzing. Okay, so that oh, sorry. Yeah, no, so I have to change. Yes, yeah. That's what I was going to change next. Yeah. So let's see. So this becomes plus x4. Yeah, okay, that's good. This is fine. And then right, like and then and the other one is just like that. X1 is 1 minus x5 plus x4. So you see now we're deciding to write everything in terms of x5 and x4, but just to make it more clear, like let's do some simplifications. So if you simplify a little bit, that tells you that x3 equals 2 plus x5 minus x4, and then x2 equals 4 minus x4. And that, I mean, there's nothing else to change here. X1. So now this is like the system of equations, and this is like these are the basic solutions, and the others are the non-basic ones. Is that okay? Is that making sense? So far, so good. And we're almost done because again, this is like the magic of this method because it also tells you the solutions. You can read off the solutions. So if you said x5 and x4 equal to 0, you would get the values for another basic solution. So if you take x5 and x4 equal to 0, the basic solution is what? Well, that you read the system of equations. X3 becomes 2, x4, sorry, x2 becomes 4, and x1 becomes 1, right? So the basic solution would be, well, it's like in the opposite order, 1, 4, 2, and then 0, 0, right? And if you look at the shadow for this point, that is 1, 4, and 1, 4, which corresponds to this corner. So that means that we should already have reached the max, and we will verify that in a moment. So this has shadow. The shadow for this of this point is 1, 4, which we already knew was the max from the graphical method, right? Which should be the max. Okay, but how do we confirm that this is the max? You have to rewrite the optimization function in terms of the non-basic variables. So to confirm that this is the max, what is like the optimization function? The optimization function was this, right? This is what the optimization function was before. And so what does that become? It becomes 6.8 plus 1.2 x1. But what is x1? X1 is 1 minus x5 plus x4, okay? Minus 1.7 x4, okay? So if you do that, if you simplify that, that gives you 8. And then, okay, so you have minus 1.2 x5 minus 0.5 x4, if I'm not mistaken. Is that okay? Is that making sense? So far, so good. And you see, like now all the coefficients are negative. So if you try to increase these variables, you are actually lowering the value. Now once, like, and in fact, that's where the simplex method that's how you would know that you terminated because all the variables are with negative coefficients in the optimization function. So that means that increasing them is actually bad. So like the most you can do is when you set them equal to 0, that's like now, so now increasing x5 or x4 actually lowers the function because that makes it like, their coefficients are negative, lowers z. So the best you can do is to set them, keep them at 0. So the best you can do is with. Okay. So, and when there are zero, that means that z had to be 8, and so that also gives you for free the value of the max. So z equals 8 is the max, and it occurs at that basic solution. 14200. So we got the where the max occurs, and we also got the value of the max. Both things basically at the same time. Is that making sense? So far, so good. I mean, this is definitely probably the most important class of the entire course, because like the entire course is just the simplex method, right? So what I'll do next time is, because I only have 15 minutes left and I want to kind of like rewrite this carefully, but I'll kind of show you what happens if you rewrite these systems of equations in matrix format. And what you will see, I'll just show you what happens for the first one, because you know, so next time. If you look at this next time, like what, okay. So originally at the very, very beginning of all this problem, right, we had started with this, right? And this was changed, right? After the first step, this was changed to, where are you? I think it had been changed to this one, if I'm not mistaken, because, right, like this is where we did this, yeah. So that was like the first like major change of variables that we had done, right? Like and then well, like I can put and then this was changed to, you know, what was this changed to? It was changed to the very last one that we had in here. So if you kind of keep track of like the systems of equations we got at each step, right? Yeah, at least I'll kind of repeat this next time because it's like one of the more important things, right? But if so, this is how the system looked at the beginning. This is how it looked after like we swapped what, x4 with x2, right? And this is how the system looks after we swap x1 with x5. We did two swaps, so that's how it looked at every step. If you rewrite this in matrix notation, how can you do that? Okay, you have to rewrite it first as like just more symmetric, like x1 plus x3 equals 3, then x2 plus x4 equals 4, and then x1 plus x2 plus x5 equals 5, right? Which gives you 1 0 1 0 0 0 1 0 1 0 1 1, right? 0 0 1, and then this is like an augmented matrix, right? If you remember those from linear algebra. So that's how the matrix, like the system looks like, right? Then how does this one look like? Like this looks like, it looks like x1 plus x3 equals 3, x2 plus x4 equals 4, and then x1 minus x4 plus x5 equals 1, right? If you find a typo, let me know, because otherwise it will mess everything. And so if you rewrite this as a system of equations, what do you get? You get 1 0 1 0 0 3. Then you get 0 1 0 1 0 4, right? And then you get 1 0 0 negative 1 1, right? And then this is a 1. Is that okay? Is that making sense? And last but not least, and I'm almost done. If you rewrite this, like you get x 3 plus x4 minus x5 equals 2. X2 plus x4 equals 4. And then x1 minus x4 plus x5 equals 1. So that gives you 0, 0, 1, 1, -1 with 2. And then this gives you 0, 1, 0, 1, 0 with 4. And then this gives you 1, 0, 0, -1, 1 with 1. Okay. Whew. And then what can you see? Like then here's the question. If you look at the matrices themselves, how are they related? For example, how is this related to this matrix? Can you find it through a row operation?
It's negative the first row minus the third row.
Well, let's see. I
Oh,
think
sorry,
no,
the
it's like
second row.
negative second row plus the third row, right? So this is related by a like like the first row was kept intact, second row was kept intact. The only one that was changed was the third row. So you kind of like use this pivot actually to cancel out this one. So you do minus row 2 plus row 3. Into row 3. Oops, like I mean it's not here, like it's in the other one. Sorry about that. Let me move it. So this actually going from one system to the other actually was connected by a row operation. And let's look at this one. How did we go from here to here? The second one is the same, right? The last one is the same. So like the only one that was changed is the first one, right? And what did we do here? Let's see, like anyone see it? Like, how do you go from here to here?
With negative the last row plus the first row.
Yes, I agree with that. Yeah, which is not at all obvious that what we were doing was kind of connected by a sequence of row operations, right? And so once you realize that, you can actually just do everything in terms of like the matrices. And that's why I'll explain you next time how to just like work with the matrices themselves. And then you don't have to, that is kind of like a more symmetric way to do it. Yeah.
Isn't it just positive row 3 plus row 1?
Oh, is that, let's see, what is going on here? Wait, let's see. Because the thing is like you make this into a 0, right? So I need this one. I need it's like yeah, like you're looking at this one here, right? So this becomes negative with 0, then 0, then 1, then this negative becomes a 1. So yeah, no, it's like the important thing is like again, highly not obvious that everything that we were doing here secretly corresponds to a sequence of row operations. And that kind of connects it nicely with the linear algebra because, but it's not, you see, like the goal is not to kind of get to the row reduced echelon form when you were solving a system in 250 because you're trying to find basic solutions. So the row reduced echelon form will not necessarily produce basic solutions. So it's kind of like a weird, I mean, not a weird, but it's kind of like a selective the row operations because you're not trying to get to the row reduced echelon form. You're trying to find basic solutions that increase the maximum of the value. But they're still all row operations. So I'll kind of like explain next time how to do these steps in terms of which row operations to choose. Because like the idea is that if you know which are the row operations that you have to choose, you can kind of like forget completely about writing the systems of equations in this way, which is a little bit more asymmetric because it requires like kind of like writing out explicitly the distinction between basic and non-basic. Here, like they're all kind of like at the same level. So it's kind of more like it's easier to program, for example, if you thought about it that way. Okay, let's stop here. I think it's like a good place. If you have a chance to rewatch this lecture, it maybe even makes sense because this is, since today is Wednesday, we talked until Monday next time, but it is like really one of the important classes, or at least read the notes because it is really crucial. Once you understand that, everything else in the course can be solved basically in one way or another. So but yeah, let's finish here and I'll tell you next time how the matrix stuff works.